Good morning everyone, my name is Lucas and I'm going to present you guys now this paper that talks about the relation between anxiety and the serotonin transporter mRNA polynylation. The serotonin transporter, also called SERT, is known to regulate the transmission of serotonin in brain tissues. This gene has two alternative polynylation patterns, so we can express the longer or the shorter mRNA. What the science knows so far is that the longer RNA is related with anxiolytic properties in mice and humans. Here, they also studied the 8N or NPK and its relation with SERT. And I call here on 810 to simplify. 810 is a heteronucleoprotein that binds selectively with the longer 3' material of SERT mRNA. This relation between each other is important because the study shows that 810 regulate expression of SERT that I'll talk about soon. Beyond, this article presents a study about S100B, a trophic factor that helps the phosphorylation of 810 that made the expression of SERT be increased. Here I want to show you the regulation patterns of these molecules. At the top, we have the two different types of alternative polynylation of the SERT mRNA. Repressed by miR16, a certain type of miRNA that can repress both polynylation patterns. However, when S100B is activated, it may upregulate the SERT expression by two different ways. In the A is decreasing the miR16. This way, the interference RNA cannot repress SERT expression. Other way to upregulate SERT expression is increasing the activity of a type of kinase, the S or C family kinase. This is a mediator of 810. This way, 810 is now able to bind to the longer mRNA of the SERT. What 810 does is simply displace miR16. This is the model of the SERT mRNA. As you can see here, it shows the two polynylation sites, the proximal here and the distal. The miR16, as I told, has complementation affinity with the proximal 3' UTR of the SERT mRNA. In B, we can see the conservation patterns of SERT, and this dotted line represents the satisfactory threshold of conservation. Here, we can see a UV cross-linking electrophoresis gel, presenting two different kinds of probes, SERT1 and SERT2. This test is for basically see if you have a similar protein that binds to the distal element of the SERT in several types of neuronal cells specified on the top. We have to pay attention on this signals on the top. Negative is reaction with labeled probe, while positive is 100-fold excess with unlabeled probe. The result shows that with SERT1 only C6 and HAC show consistent results, while SERT2 is visible in all the cell types. Then the result is basically that the same protein can bind to the distal SERT in different cell types. This graphic is showing an RNA immunoprecipitation presenting the relative abundance of 810 in each tissue type. Here we use the RNA of 810 as negative control and the COX as a positive. COX2 was already proved to bind positively to 810. After the qPCR, we can see that the SERT ribonucleoprotein binds to SERT more than 810 control. This is valid for all these three kinds of tissues. What we can see here is that A10 ribonucleoprotein binds positively with SERT, mainly in distal polydinylation SERT. What happened if we knock out the gene that expresses A10? What basically happened is what we expect. Either the A10 and SERT proteins production are decreased. This is what you can see here. In A is a Western blot contrasting with the wild type and treated with a short hairpin RNA that interfere with the expression of the two proteins. We can see that the proteins in treated cells does not express so much compared with the wild type. B and C shows protein quantification of both, and we can see that the amount of protein in wild type is greater than treated cells in all the cases. Now we're going to start to talk about S100B, a neurotrophic protein that increases the expression of SERT. This protein acts as an activator of phosphatidylserine. Phosphatidylserine is a kinase that phosphorylates A10, and this last, once phosphorylated, increases the expression of SERT. So let's explain it in parts. In A, we have an immunoblotting of these proteins. Here, beyond the negative control, you also have cells treated with S100B. Furthermore, we also have cells treated with PP2, a kinase inhibitor that inactivates phosphatidylserine. This way, phosphorylation of A10 is inactivated, inactivating expression of SERT. We can also improve it in B, that is showing expression of SERT with different treatments, showing the same pattern than in A. In C and D, we can realize the same logic than in A and B, but now this is for phosphatidylserine. This immunoblotting is showing that only cells treated with S100B the phosphatidylserine is expressed, and when we have treatment with this kinase inhibitor, the phosphatidylserine is decreased. This protein quantification is showing the amount of phosphatidylserine in different situations, and we can see, as we saw in C, only cells treated with S100B express this kinase. And finally, the researchers also worked with miR16, mRNA that can repress SERT expression. miR16 pairs with the proximal 3' UTR. However, what they found in this work is that A10 can displace miR16, resulting in increasing expression of SERT. The technique is a little bit long. I choose not to communicate with it because if I do that, I'll not finish this today. But basically what they did was to measure the amount of miR16 in each situations, using biotinylated 3' UTR of SERT mRNA and radically labeled miR16. The result is that the expression of miR16 is smaller in the presence of A10, suggesting that this last one protects SERT mRNAs. However, it only happened with longer SERT, seeing that A10 RNPK only binds to longer 3' UTRs, and this way displacing this miR16. So what happens basically, we have the longer 3' UTR here, and we also have the shorter SERT, the shorter 3' UTR of SERT here. But we also have the miR16 that likes to the repressed expression of the shorter cert. But now we have the A10 RMPK that displays the miR16 now. It binds to the longer 3' material of the cert. So it's basically this what happened. The A10 protects the cert expression. And the conclusion of all of that is that we can use this kind of study to develop different kinds of anxiolytic drugs. And I thank everyone for watching, and I hope everyone understood. Thank you.